So in this video we will study about the calculation of K or equilibrium constant. For an example, if we have this reaction which is a N2O4 decomposition into NO2 gas, colorless to brown, the table shows the below provides the equilibrium concentration for reactant and product. Calculate the equilibrium constant for Kc. So when this type of experimental detail is provided, there are 4 experiment was done in where initial means these are the reactant concentration. Here is no reactant, here is no reactant, here is the one reactant, and the equilibrium concentration is given. So once in calculation of K we always use equilibrium concentrations. These one are important, right? Now we don't use the initial concentration. So what we can do, we can calculate equilibrium concentration for Kc for one experiment and Kc for 2 experiment. So let's see what we can do. So we can write Kc1, and as we know the product which is NO2 for my first forward reaction divided by reactant N2O4, and then here we can add the values. Basically the values for the first experiment will be, product will be 0.0172 and in the big parenthesis raised power 2 divided by the reactant concentration which is 0.00140 and big parenthesis, right? So once we will do the math of this raised power, it will come 0.000296. I have already calculated, that is why I am using this number, and here will become remain, there is no power, so 0.0014. and once we will divide these numbers, we will come back like 2.11 times 10 raised power minus 1. You can double check if I am doing correct or not. So this is the one experiment. Let's calculate the experiment constant number for 2, right? Kc number 2. So for Kc number 2 we are going to use these values. For Kc number 2 we are going to use these values, which is for experiment number 2. So this will become 0.0243 raised power 2 and then divided by 0.0028. So this will become, once we will solve this math, will end up at same value, 2.11 times 10 raised power minus 1. So since Kc, you can see Kc in the experiment number 1 and 2 is constant, so look like we got the equilibrium, and this is the way we calculate the equilibrium constant for any reaction. You have to include all the coefficients as a power and then do math. So this was the one example, and then next part is the equilibrium constant in terms of pressure. So we have seen in the previous previous video, then when we have homogeneous expression written in the gaseous form, I was usually writing as Kc, but rather than Kc I should write Kp. So P represent for pressure. Since pressure is the proportional to the concentration of gases in a closed system, the equilibrium expression can also be written like Kp equal to capital P for pressure of C gas, which is product, capital P pressure of the D gas, which is another product, and then raised power of small c and small d as their coefficients. So these are the coefficients which will go as a power, and divided by reactant gases pressure and their power. So this is again exactly same, Kc and Kp exactly same. The only difference is here, this is in the concentration and this is in the pressure. So but there is some relationship between these two, and we will derive what is the relationship here. So once again, whenever we write, this will be product divided by reactant always, and then coefficients. So how we can establish a relationship between the Kc and Kp? So we'll see in the next slide that relationship between Kc and Kp. So let's continue this reaction. A small a, capital A small g, and then these are the reactant, these are the product, C and D are the product. So from an ideal gas law, so if you remember the gas chapter, we know the ideal gas law is PV is equal to small nRT. P is pressure, V is a volume, small n is number of moles, R is a gas constant, T is temperature in atmosphere, Kelvin. So rearranging it, we get, so we can rearrange this equation. So after rearranging, but basically what we are doing, we are moving volume to the other side, right hand side. So we can write small n over V RT, and small n over V is nothing but the molarity. This is molarity. Molarity means moles over volume in the liter. So we can rearrange this equation like this also. Capital P equal to mRT. M is molarity. Now if you will see the from previous expression where we were writing this Kp equal to Pc, so we can rewrite this expression in this little bit. We can also write capital Pa in terms of concentration, where concentration of A or molarity of A, this is the molarity of A, and RT, right. In the same way we can write the molarity of other reactant also. We can also write other reactant also, and we can write Kp will be equal to, so let's look at our slide again, the previous slide. So we can also write this C, for C this will be capital C RT small c, and then capital D small d RT divided by capital A is raised power small a RT, and big parenthesis of capital B small b RT. So what we can do from here, we can, you can see capital RT is common in both numerator and denominator, so we can take a common. So we can do like this one, capital C divided by capital A multiplied by capital D and capital B, and small c, small d, small a, small b will be coefficient as a power, and RT I can take common, RT over RT. But here we can also move these small c and small d, small a and small b outside, so we can remove from these coefficient outside. So what we can do, we can write like this one, c plus small d and divided by a small a plus b, right. So if you know, if you remember the Kc, so this is basically, this is nothing, this is Kc. So what will be the relationship between these two? So here this is my Kp. So Kp we can write Kc, and then RT we can take a difference. So what is the difference? Small n raised power n, and small n will be c plus d minus a plus b. So this c plus b minus a plus b will be delta n. So we can establish the relationship between the Kc and Kp like this, that Kp will be equal to Kc RT delta n, where delta n is equal to total number of moles of the product minus total number of moles of reactant. So moles of gaseous product minus moles of reactant product. So the subscript P, small p, stand for pressure, and atmosphere are always in the pressure calculation, right? So this is the we establish the Kc and Kp relationship. And next is let's see one example to understand this calculation. For an example, in this reaction you can see Kc, for this reaction the value of Kc at 472 degrees Celsius is this much. Calculate the Kp at this temperature. Okay, so Kc is given, which is 0.105, and temperature is given in 472 degrees Celsius, which we need to convert into Kelvin. So what we can do, we can add 273, that will be equal to 745 Kelvin. And now we have to calculate Kp for this reaction. So this is the Kc is given, and Kp we know, we have just established the Kp-Kc relationship. So this will be Kp equal to Kc and then RT delta N. What is delta N here? So if you remember, delta N is equal to product, moles of product minus moles of reactant, right? So moles of product, how many moles of products are there? Product is ammonia only, so this is 2, minus, and total reactant mole here is nothing, basically it is 1. So 1 and 3 plus 4, so 1 plus 3, 4, so 2 minus 4 equal to minus 2, right? So delta N is my minus 2. Now we can place the value 0.105, and then R value is constant 0.0821, atmosphere liter mole per Kelvin multiplied by 745 Kelvin, and delta N will be minus 2 raised power minus 2. So Kelvin cancel out, mole mole will remain here. Okay, so now we have to do the math. So once we will multiply these two and take a minus 2 power. Minus 2 power means under root basically. So you have to do math in the calculator, which I have already done, and then 61.16. You can double check if I am doing correct. So this, okay, this is the product, and then now I am going to solve this math. So total answer will come 2.81 times 10 raised power minus 5 Kp. So this is the way we can solve this question, how to calculate the Kp if the Kc is given. So now let's generalize this Kc Kp equation, and there are some important guideline. Equilibrium constant Kc and Kp guideline, always product over reactant. So Kp or Kc is always written as product over reactant, right? Always use appropriate subscript. Never include solid, pure liquid we do not include. Remember heterogeneous equilibrium constant. When using Kc, always use concentration in the unit in molarity. So basically we use big parenthesis. Big parenthesis means molarity. Never include solvent in the expression. If the water is written like this one, H2O, any form, any solvent which is written small l, never include these also. Using Kp, always use pressure unit in atmosphere, right? So these are some important points. And then next important thing is this that equilibrium constants are defined, they are unitless. right? Equilibrium constant do not have a unit. Equilibrium constants are always positive, and equilibrium constant can vary in size, very small and very large. So this can be like 1 or 0.1. We have seen one example, or 0.01, or they may go into, when we calculate pH, they go into -14 or 10 is power -11 or 10 is power -3. So these are very very small. They can also be in a very large. They can be like 10, 100, or they can be in 10 is power 4, 10 is power 5. So we will see some more math and manipulation in the next video about the equilibrium constant calculation.